All right, welcome back. Today we're going to be talking about vectors and a little bit about vector components to help you better understand what they're all about. So we'll start off with the simulation here. This online simulator lets me sort of drop in a vector and we can explore some of the things that it can do. So vectors are a mathematical abstraction. By that, we just mean it's a thing that we created to help us manage the complexity of this concept, this idea that you can have a measurement, a physical quantity that has an amount, magnitude, and a direction. Now, when we want to represent that on a piece of paper with a drawing, what we often draw is an arrow, right, with a certain length pointed in a certain direction. And what makes a vector special is it's not just any old thing that it has an amount, a magnitude, and a direction. It's that it has this special property that if you rotate your head in either direction, the vector doesn't get longer or shorter, and it doesn't change the direction it's pointed, right? Rotating your head doesn't also rotate the vector on the piece of paper. And when we think about our vector, we really do want to think about it as just an amount pointed in a particular direction, okay? Now, oftentimes, right, so if, let me go into my drawing here, we have our vector here, and let's say I might label this vector, I'm gonna follow what we have over here, I'm gonna label this vector A. And I just throw that little arrow up top to show that I'm talking about a vector. This is not just a regular number, it's a vector. And I don't really label the direction right now. And I don't label the direction because I've just physically drawn it. I could draw in a different vector, maybe this vector B, okay? And well, what's different about vector B? We can see vector B is shorter, so we might say its magnitude is less. And we can also say it's pointed in a different direction. Right? I can also take a vector and scale it. I can make it longer, or I can make it shorter. So let's imagine vector C is some number times vector B. And let's say I want that amount I'm multiplying by to be the number 2. Well, so then that would mean I would draw a vector in the same direction, but double the length. And this would be vector C. And you can start to see another property of vectors is that where they're drawn on the page doesn't affect its two properties of its magnitude and its direction. B and C both point in the same direction. And this is a common strategy we might use where we don't draw the vectors right on top of each other, but if we wanted to, we could move them around on the page and see, yes, that vector points in the same direction and it's twice as long, okay? And so again, I can move this vector around anywhere I want on the page and it is still true that it has the same magnitude in the same direction that it did before I moved it. That's an important property of vectors. Now, we can do a whole bunch of things with vectors just by drawing them and connecting them and placing them tip to tail. And in fact, when you look at the vector addition, you'll see that is a way that you can work with vectors just graphically, just by drawing things with rulers and protractors. But of course, that's not the best, most efficient strategy. If you were designing a bridge or a building, you would not want to have to draw every single vector in order to figure out your situation. And so we introduce this idea of vector components. Before you can have vector components, you have to have a coordinate system first, okay? And you get to pick that coordinate system. Now, oftentimes you might say it's been chosen for you. So if you look at our simulation here, you'll see here is an X and a Y coordinate system that's been chosen for us. But it is still possible for me to move, right? To move that coordinate system around, or it's even possible for me to rotate that coordinate system. That's a little bit of an advanced strategy, but that is something I can do. And the moment I do that, I can then talk about the components of the vector. What is the stuff that if I add them together creates my original vector? And we choose them in a way so that they align with the coordinate system. So something like this. Here, I have this little arrow here that points along the x direction. Okay, that is as much as vector A points in the x direction. Okay. And I have this piece over here that is pointing just as much as the vector is pointing in the y direction. Let me draw that nice and big over here so I can label it. So here I have vector A, and I have this component here, and I have this component here. Now, one of the things you'll notice is that they're connected tip to tail, okay? You'll notice that vector A is the long side here. That's pretty standard. And we can also start to label these different components. Now, if for this part that is pointed along the x direction, we might label that AX. And for this part along the y direction, we might label that A sub y. Okay, the x component and the y component. And in the same way that you can move around the original vector and not change the result, its magnitude and its direction, you can do the same thing for the components. So you might see components drawn like this, right, where all of the vectors are all starting at the same point. Okay, you might also see the vectors drawn in this way, where you're simply showing that they align to the x and to the y axis. And again, as I move this around, it's almost like casting a shadow. You can imagine a light shining from up here, and this is the shadow that the vector would cast on the x-axis, and this is the shadow that it would cast on the y-axis. Now, I like to think of the components in this way, because that helps us connect, well, what is the relationship between the original vector and its components? And if you look at this triangle long enough, you should notice that it is a right triangle. It is a right triangle. And that's on purpose. Our coordinate system had right angles in it, and so our vector components are going to have right angles in it. That's all done on purpose. And so there's a connection between the original vector, right? The original vector and its components. It's the rules that connect the hypotenuse of a right triangle with its legs. Okay? And so we can use this relationship in either direction. If we know the AX and the AY, we could figure out the original magnitude, or we could use this trig sort of in reverse to go in the other direction. We also know that there's a relationship between the angle, okay, that the vector makes with the x direction, right? And so if we go back and think of our triangle, we have our hypotenuse, our opposite, and our adjacent. Here's the angle theta that we want to figure out. And if I write down my trig of relationships, okay, I see that if I just want to figure out the angle in terms of the adjacent and the opposite side, I'm going to write this as the inverse tangent or arctangent, depending on what your teacher called it in your math class, AY divided by AX. Okay? And so that's how, if we start with the components, we can figure out the original vector and the angle that it makes. But again, this angle only depends on the coordinate system. If I had flipped x and y, the angle would have been different. Or if I rotated it slightly, the angle would have been different. So the angle is like a made-up thing, but you might see in a question like this vector makes an angle of 30 degrees above the x-axis. 30 degrees above the x-axis. So you just have to draw your picture carefully there. We can also go the other direction and say, well, what is AX and what is AY based off of the original vector A and the angle that it makes? And to do that, we're just going to go over and use our other two trig identities. And so in order to figure out the x component, I'm going to take the original vector A, and I'm going to multiply it by, well, the x component would be the adjacent side, so I'm going to use cosine of the angle. And the y is the opposite side of the triangle. And so I'm going to use a times the sine of the angle. Okay. And so whether I start with the original vector and I want to figure out the components, or I've got my components and I want to figure out the original magnitude and the angle, I can use trigonometry to figure that out. But again, it all comes back to this original drawing here where we are figuring out the sort of these sides that are parallel to the corresponding axis. And you can see how as I drag and move this vector around, you will see the components, they will change, as well as the magnitude and the angle that it creates. All right, see you next time.